Hey everybody, welcome to Gridspace / MIT IAP. This is lecture number 4, and we're going to talk about subtractive synthesis. My name is Nico. My primary job at Gridspace is making the IAP website. And I also own a synthesizer, so that qualifies me to talk about this topic. So we are, technically today is the 14th, right? So we're a day behind. Do we get back on track? Okay, tomorrow? Okay, awesome. So if you're just tuning in, the first lecture Anthony talked about engineering a song from scratch, just using sine waves. Then we talked about acoustics and signals and some of the theory behind that. And then we had noise engineering as a special guest yesterday talking about modular synths. And so I am also going to be doing mostly a synthesizer demo. The main purpose of this is just to make noise. I'm going to gloss over a lot of the more theoretical aspects. I'm not an electrical engineer, so I'm really just a guy with a synth. The goal is going to be to mostly just introduce the concept of subtractive synthesis. And then I'm just going to walk through this instrument. And hopefully by the end, you'll understand what most of these knobs do. And this is a great kind of introductory synthesizer because it's got most of the basics and it's pretty straightforwardly laid out. So I think it's a good challenge to see if by the end, people kind of understand what they're looking at here if they're not familiar with synthesizers. I'm not going to stop for questions, so if you have any, just shout them out or raise your hand or look them up on your phone and then shout the answer. Okay, so subtractive synthesis. So we've already talked about additive synthesis, where you plop sine waves down at different frequencies and you can create technically any sound from doing that. And so that, by analogy, is similar to painting additively on a canvas, right? Just adding paint. By contrast, subtractive synthesis, we're going to start with some noise ore, and then we're going to sort of like filter it down and remove stuff until it gives us a sound that's hopefully pleasant. So this is the Korg mini log. This is an analog synthesizer. It's a fixed architecture synthesizer. So noise engineering yesterday was demonstrating a modular synth. And so unlike that, all of the connections to this are fixed in place. So you don't have to plug in patch cables to send inputs to outputs. But, you know, so it's a little bit less flexible, but you'll see it's actually still very versatile, and it's a little bit easier to get something that sounds good to come out of it, right? You're not going to have the problem most of the time where just, you know, you press a key and nothing happens and you have to like debug your circuits. In this case, it's just plays more like an instrument. This is a analog synthesizer, so most of the components are actually analog electronics. It's I think, except for a couple of features, not sampling this, so which is good because we're talking about sampling theory later. So this is just generating voltages with analog electronics, resistors, capacitors, and whatnot, and then sending them through various filters, and then producing just sound directly versus converting to digital and then reconverting to analog. This is a 4-voice polyphonic synthesizer, so that means that I can play up to 4 notes at the same time. And if I play more, what it's doing is actually removing the earlier notes that I played. So it kind of feels like you can play more than 4 notes, but really what it's doing is just halting earlier notes that you played. And you can kind of see this is the block diagram of this entire instrument. So this is kind of all you need to know. But you see this whole circuit here is just copy pasted 4 times. So that's why there's limits to how many different notes you can play at the same time. In theory, it'd be nice to just be able to play as many as you want, but you would have to replicate that circuit for every note that you wanted to play simultaneously. So this is 4 notes is a good trade-off. A lot of synthesizers are actually monophonic, which means you only play 1 at a time. And so this is kind of controls the cost of it, but at the same time you get a good kind of musicality to it. So the principle of subtractive synthesis is you want to start with some kind of like noise ore that hopefully has interesting harmonic content, and then we're going to filter that out. And so if kind of the way that this the circuit is laid out in this diagram is very similar to how it's laid out on the device itself. And it's unfortunate that you guys here can't see this. That's going to make this a little bit more difficult. But basically, on the left side of the instrument are things that generate tones. And then when you move towards the middle, then these elements of the instrument subtract back out certain parts of those tones. And that results in sort of more musical tones. And then as you move further to the right, there are envelope generators, which can kind of further shape the volume of the tone over time. And then there's a few filters on the end. So you can see that kind of on the left side. So VCOs are what are known as voltage controlled oscillators. So those are the oscillating elements that actually generate noise. And then most of these components here, right to the left of this VCF block, are all about changing the shape of those oscillators and causing them to interact in different ways. And the reason that you do that is to create more interesting harmonic richness to the sound before it gets filtered. Because then once you've generated that tone, you're going to be just amplifying or reducing different parts of the harmonic spectrum. All right. So these are kind of our basic building blocks on this synthesizer that we can use to create sound. So this is our friend, the sine wave. So, you've seen this is the time domain graph of the sine function on the left, and then on the right is our harmonic diagram of it. So you can see there's just an impulse at the frequency of the sine wave and no other harmonics. Actually, there's no sine wave on this instrument, and just kind of think to yourself about why that might be. Like, a sine wave's pretty easy to generate in electronics, so why not put a sine wave generator on here? This actually only has 3 options for each oscillator: a triangle wave, a sawtooth wave, and a square wave. So this is the sawtooth wave. And so you can see it's got a base frequency, and then at multiples of the basic frequency are the harmonics, as we've discussed. Now, there's no reason why it has to be a base frequency with harmonics. You can generate, whatever spectrogram you want. But in the case of a synthesizer, these are really common oscillator types. And the reason is just that they sort of correspond to the types of harmonic signatures that you might encounter in real instruments. So, having a base frequency with harmonics is a property of a lot of instruments that are based on, wind or strings or other, solutions to the wave equation. So it's just a good starting point if you're interested in generating musical instrument-like sounds. So let me just, here, let me set this to, sorry. So that's the sine wave. So some people say that sounds like brass, I guess. this is the square wave. And so you can see the spectrogram of the square wave is different. So we're missing all of the even harmonics. And so there are a lot of instruments where the even harmonics are reduced, or, you know, normally they're not completely gone, but you can add this with other elements to kind of create wave shapes where the even harmonics are reduced. So that sounds like this. And that's supposed to sound like a woodwind instrument. And then the last shape of the oscillators are triangle waves, which kind of, by their shape, sound a little bit like sine waves. And you can see it's the same as the square wave, where it's only got the odd harmonics, but they're reducing a lot faster, right? So it looks in the harmonic diagram, it looks a lot like a sine wave, right? It's just got a little bit more of those overtones to it. And so as a result, it has that kind of smooth, kind of like video gamey sound. And then this is noise. And this synthesizer actually has a noise generator. So if I turn down the oscillator, you can just, and you'll notice that, you know, no matter what note I press, it sounds the same. Noise is noise. And then this is the time domain, and then that's the frequency domain. So the Fourier transform of noise, or white noise, is noise. So those are our basic components. There's a few different alterations that we can make to those waves that are available, again, on the left side here where we're generating tones. So, first of all, there are two oscillators that are available, and we can mix them together. And so, let me just... So right now, they sound pretty similar because they're both the same waveform type, but we can do things to make them sound distinct. So one thing we could do is change the shape of the second oscillator. So now we're getting a sum of those two sounds, which is kind of nice. You can change the pitch of one relative to the other. And there are some, you know, in most physical instruments, there are, you know, elements that are out of tune with themselves or each other. And so having things be perfectly pitched is less harmonically interesting than having them be a little bit offset. And when Anthony was programming his MIDI synthesizer, I asked him to detune one of the sine waves just to, like, kind of give it a little bit more of a natural feeling. So you can do that. On this synthesizer, there's something called shape, which basically for a square wave will change the pulse width. So imagine, you know, that square wave. Actually, don't imagine it. Look at it. So see how it's at 1 half the time and -1 half the time? You can change the oscillator so that it spends more time at 1 or less time. So maybe it's like 90% at 1 and then it dips back down. And what that's going to do is change the frequencies and the harmonics that are expressed. So instead of having no energy at the even multiples of the fundamental, it'll have a small amount of energy, and then that increases as you decrease the percentage of the width of that square wave. So I'll show you what that sounds like. So this is just our normal square wave, and then you can see it gets a little, like, kind of more harsh sounding maybe. it's got that kind of buzzy sound. Okay. Actually, before I do that, let me talk a little bit about other ways to shape it. So this has a setting called a ring, or sorry, sync, and that takes the second oscillator, and every time we get to one cycle of the first oscillator, in term one period, it resets the second oscillator. And so what that looks like is, it may be at some part of its waveform, and then it'll all of a sudden jump back to the previous part of its waveform. So if you have, for example, a sawtooth wave, if the first oscillator is, let's say that it's playing at a frequency that's a little bit lower, then what you're going to have is this amplitude's going to go up. It's going to get, go back down to the bottom of its period, and then it's going to get maybe, let's say, halfway up, and then the period of the first oscillator is going to be reached, and then it's going to jump back down to the bottom. And so you'll get this alternating pattern of big triangle, little triangle, big triangle, little triangle. And again, that just adds some harmonic richness. So I'm going to set these both to be sawtooth waves. And then we're going to just do it with and without sync turned on. So let me just set the volumes here. So that's just the two sawtooth waves playing. And then if I turn sync on, it sounds not that different, but we can change the pitch to tune one relative to the other. I don't know if you can hear that. But it kind of has a similar effect to the shape change, where it just adds extra harmonics. Okay, so that's kind of an overview of the ore of the subtractive synthesis. So all of this stuff was really just generating a sound with lots of harmonics that are roughly musical, that sort of mimic is how instruments work. And then the next step in the instrument is the filter. And so this is a diagram of an ideal low-pass filter. So basically, this is in the frequency domain. So you can see, like, in an ideal world, a low-pass filter would multiply the frequency domain of your signal by this step function here, where everything below some cutoff is just multiplied by 1, and everything above it is multiplied by 0. And so basically you would just be left with the lower frequencies. If you remember, multiplication in the frequency domain is the same as convolution in the time domain. And so if you take the inverse Fourier transform of this filter, you get the sync function. And so basically, if you convolved your time domain signal with this sync function, which goes on infinitely in both directions, then you would have a perfect low-pass filter. But because, number one, you don't have an infinite signal, and number two, we're constrained by what is practical in analog electronics, we're not going to get a perfect low-pass filter, which is actually a good thing in this case because, we're making art here. It would be a very boring synthesizer if we just dropped out high frequencies. So, so instead, the filter looks something like this. And so this is a resonant filter, which means that the output is fed back in. And so it can actually interfere with itself. And so as you see, as we approach the cutoff frequency, it actually boosts those amplitudes, which can create a really interesting sound. So you see it sort of curves up. There's a little resonance boost at the cutoff frequency. and then it slowly tapers off. It's not a like harsh edge. And you can actually adjust by selecting a different filter whether or the rate at which that cutoff happens, and so that can create different sounds. So let me just show kind of what that sounds like. So sorry, here's I'm gonna reset it. So this is just the sawtooth wave. And then this giant knob here is changing the cutoff frequency. So I'm moving that frequency left and right, and you're gonna hear how you hear more of the high frequencies as I move the cutoff higher, and then it just sounds more bassy as I move it the other direction, right? So there's almost nothing there because this is not a very low note. Let's actually go down a couple octaves. And there's those high frequencies which make it kind of sound more metallic. So another thing we can do is change the resonance, and we get this weird sort of like boost in these higher frequencies. And one thing that you can do with this is if the so this component will actually self-oscillate, so it'll generate a sine wave just on its own. So it acts like an oscillator if the resonance is high enough. So I'm just going to turn down the oscillator completely, and you'll hear just, here we go. So what's going on there is this filter is self-oscillating at that resonant frequency. And when I change the cutoff frequency of the filter, it's changing the pitch. And so you get that cool kind of like R2-D2 sound, basically. And on this synth, it has key tracking. And so if I turn that on, what that's going to do is, rather than me manually changing that cutoff frequency, it's going to map what key I'm playing to the cutoff frequency of this filter automatically. And so I can play that resonance like its own instrument. So there's the sine wave that we were missing before. And now I don't know how to get back. Oh, right. Okay, cool. So after our low-pass filter, this middle section, which you can't see, is the envelope generator. And so I think mentioned this in another lecture, but this is sort of the standard envelope model. And I'll just talk in slightly more detail about it, but basically there are 4 values, and what is sometimes confusing about it is 3 of these values you're modifying in the time axis, and then 1 of them you're modifying in the amplitude axis. So for example, attack, if I change this knob that says attack and make it bigger, what that's doing is moving this line to the right. So it's making the attack take longer. So you can see as I hit the key down, it's taking a long time to get to its full volume, and if I make that smaller, that time changes. Decay is the same thing. So once it gets up to its full volume, it's going to change direction, and the amount of time that it takes to go back down is determined by the decay. So you'll hear it kind of goes back down. Sustain says what the height of that plateau is. So if I set sustain to 100%, then it never decays back down. And if I set it to 0, it's going to go back down to silent. And then the last one is release. So that's just after I let go, how long does it take before it decays back down to 0? Obviously, if sustain is all the way down, then release doesn't do anything. So there are 2 envelope generators on this machine. So one is what I just showed, which is the amplitude envelope generator. So that basically is just the volume over time based on when I press these keys. The second one is a semi-modular envelope generator that can be changed to affect different other attributes of this. So for example, I can make this envelope generator change the pitch of the second oscillator, and so that's going to make it go like woo when I like press the keys. So let me show you what that sounds like. There we go. So technically I could do all of this just by like having more hands and like doing this with the knobs, but having the envelope generator sort of automates what you would normally do, and it just frees you up to be creative in other ways. Let me go back to the diagram for a minute and just let's sort of recap where we are. So again, on the left side, we've talked about the 2 oscillators. We talked about the shape filter, and so that's just changing the harmonics. We talked about the noise generator. We've talked about the, where did the sync go? I guess sync is not on this diagram.
Is it not Osc sync there? In the top left, kind of?
Oh, yes, there it is. Osc sync, yeah. There is a cross mod operator, which I didn't talk to, that does FM synthesis, which will be the topic of the next lecture, so we'll skip that. So then we've gotten so everything up to pre-VCF mix is kind of, again, just creating those interesting harmonic overtones, and then the VCF, which is the sample voltage controlled filter, is our low pass filter, which kind of subtracts out some of the harmonics. And then this is the envelope generator, which you can see feeds into multiple things. So the pitch one, which I just showed, is this connection here, which goes back to the pitch of the voltage controlled oscillator there. And then the other thing that the envelope generator can impact is the low frequency oscillator, which I'll show us actually one of the most fun things. So this is just another oscillator, but it is low frequency, as the name suggests. And so rather than hearing it as a pitch, you just hear it as an oscillation of whatever the parameter is. So you can, for example, make it impact the pitch. And that's kind of similar to what we were doing with the envelope generator, but in this case, instead of an envelope that's affecting it, it's just another oscillator. And so this can actually be a square wave. Sorry, rate's too slow. Okay. So that's our square wave. Again, outside of the audible frequencies, so we're just hearing that as on and off. Here's a triangle wave. And then here's our sawtooth, and just imagine what this is going to sound like for a sec before I play it. So that was our low frequency oscillator, and it was plugged into our pitch. But we can also modify other attributes. So we can also change the shape. So that's a little bit more of a subtle effect. Again, it's changing that pulse width of the square wave to be wider and less wide. And so you're just basically changing the amount of each harmonic over time. And so it gets that kind of like, it's almost like a vibrato or something. And then we can also plug that into the cutoff of the filter. So I don't know if you can hear that, but it's basically changing the cutoff frequency. So we're hearing alternating low frequencies and high frequencies, and you can do like really fun stuff with that. Like if you just want to be Fatboy Slim. Okay, and so that's kind of the last step on the train, and then on the very last step of the synth, we have a high pass filter, and generally that just kind of makes it sound like it's on the radio. Here, let me clear that out so you can hear just the effect of that. And there's also a feedback loop, so you can kind of get an echo effect. There it goes. You can hear the feedback, or yeah, the echo effect there. So, yeah, so one interesting thing you can do is look at frequency spectra for various instruments, and then try and figure out, like reverse engineer how you might create a sound like that on the synthesizer. So for example, like, you know, if we're looking at a flute, say, it looks like we've got, I can't tell if, so the first harmonic's really strong. There's a really steep cutoff after that. And it looks like maybe the odd ones are a little bit more prominent. So you can see like this fourth and sixth harmonic are very low. So if we just kind of go back to like, what's our or, you know, to me it kind of looks like, what is this, the triangle wave. And so you could maybe start, if you were wanting to reproduce like a flute sound, you might say, okay, well, like let's start with a you know, a triangle wave. And already that's a little bit flute-like, but we could, you know, further refine that by maybe saying, okay, like we want actually some of the even harmonics too. So what if we just added in like a square wave as well, just to give, but at a lower volume, so that those are. Right, and we might want to change the pitch on that just so it's a little bit more, a little less perfect sounding. And then another thing we might want to do is try and add some vibrato to that, just because we know flutes have vibrato. So we could change the pitch with the low frequency oscillator, like that. It's very easy to get spaceship sounds, which is really. So what I'm doing is turning down the intensity of that, so it's just a more subtle effect. There, now we got a nice little vibrato. Let's try adding the filter to maybe drop off those higher frequencies a little bit more. So, you know, it's not an exact flute sound, but it can kind of give you some inspiration for how to create sounds. So yeah, that's mostly it. Did that make sense? Any requests? Wonderwall? Yeah.
Is there anything that I don't? You mentioned the shape thing, but like anything that does sort of like a clip or soft clip to the waveforms? Is there any way to do something like that or engineer that?
Like a clip, as in trying to remove.
Or like distortion, basically.
Not on this synthesizer. I mean, the main way that you would remove frequency bands is with the high pass and the low pass filters.
Oh, I mean, like,
But
yeah, like volume, amplitude based clip.
oh, yeah. I mean, you can overdrive this thing for sure. Let's see if we can get it to clip. We're gonna probably want to do. It's actually doing a pretty good job of. Never mind, it's not clipping. I just had a bad connection before. Yeah. Anybody else want to hear anything? Yeah, that's bad. Let's hear some presets. How about that? Nah. All of these are too weird for jump. I need to get down into the lower note. Yeah, one other thing that kind of creates some interesting sounds is, so I've been basically playing this entire time in polyphonic mode. There are various other modes that have to do with which keys attack when you play them. I think the most different sounding of them is unison mode. So when I play that, it's basically, instead of being a polyphonic synth, it's going to monophonic, and it's hitting all four of the voices, like with the same note whenever I press it. And in theory, that does nothing because you're just adding the same signal. But because of the imperfections in the circuitry, it kind of gives it a bigger sound, right? Where those harmonics aren't exactly lining up. So some of the let's see if we can make kind of a bigger sound. That's just the most fun thing, is just play with the colors. Oh, that's kind of... You can all go home. No.
What's the shape do to not a square wave? Does it do anything?
Yeah, there's actually a diagram of it here. Okay, it's kind of hard to see, but so this is square wave. So see, it's changing the width of that pulse. For triangle wave, it's kind of doing a similar thing to what it was doing with the sync, where it's basically double creating two peaks, and then the height of that second peak is determined by the shape. So it kind of like it's like it inverts the top of the mountain. And then similarly, I think this is reflecting it. For Sawtooth, I think it's reflecting it and then like adding together, something like that. I don't know harmonically what that does, but usually it just makes it more chaotic.
So is it kind of making use of the like imperfect response of the low pass and the high pass filters for like kind of two peak selection almost, like resonant frequency selections?
For the shape?
For the harmonic, for the frequency shape.
Oh, for the low pass filter.
Yeah, in like digital filters then, is it, or digital subtractive synths?
Mm-hmm.
I'm imagining you might have more kind of weird shapes that you could kind of.
Yeah, I mean, you've seen what aliasing looks like in a so the artifacts from a digital low pass filter, if you've seen what it does, it kind of creates these like lobes. So similarly, even in digital, you can't have a perfect low pass filter, but that is more from the limitations of sampling than it is because of the limitations of analog electronics.
Is there like a looping thing on that synth? Like if you wanted to have a bass line while you were adding in other.
Yeah, there's a sequencer on it, which I didn't talk about because that's just sort of automating key presses, and I tend to just like to anyway. But yeah, you can record. It's a very basic sequencer, so you can't make very complex melodies. But if you just want to loop something, another option that it has is an arpeggiator. So what that does is if I turn that on and like let's just play. So that's just going to play all of the notes that I'm playing in a sequence up and down. So I don't know. That's for babies, though.
Do people try to learn to like properly shred on these things, or is it mostly about making?
So this has a really small keyboard, so it's really not like I don't think anyone's going to perform directly on this, but this can be plugged into other things, right? So if I were going to live out my dream of being a rock star, then I would have a full size keyboard, right? And then that would plug in to this as a controller. And so then like it can take MIDI in. So I would take a MIDI signal and that would replace this built-in keyboard here. Thanks.